Combustion reactions is the first one to look at. Combustion of propane, for example, would look something like this here. C3H8, we know what propane looks like, of course, with oxygen gives us carbon dioxide gas and water, of course, and you'd want to balance that out, etc., etc. Okay? If you wanted to write it out structurally, so a structural diagram equation looks something like this. Please know what this looks like. Okay? So make sure that you're able to do this, because I'm going to ask you to do this at some point in time. Give me a structural diagram equation of this. So you would write out condensed structural diagram of what is this, propane here, I said, and oxygen, of course, there's a double bond there, don't forget. Carbon dioxide, CO2, has double bonds in it, and water, of course, has single bond H2O. Okay? Yes? We remember that from Chem 20? All good. Yeah? All right. So that's what a structural diagram would look like. Okay? There we go, right into it. Let's dial it up. Here we go. Do this. Go. You should be able to do this. All right. So there's some methyl cyclopentane. Let's figure out a formula for this. That'd be what? C6. 1, 2, 3, 4, 5, 6. H. There's 1 there. There's 2 there. 2 there. 2 there. And 2 there. So what is that? 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes? 12? Is that right? Yes? Good? It's a combustion reaction, so let's do that. We can do that, hopefully. And an oxygen gives me carbon dioxide and water. Let's see, 6. So 6 here, 6 there. That's at 18, so that's 9 there. Yeah, good. All right, awesome. Easy part. Well, maybe, maybe not. Hey, good. That's it? No, well, not quite. All right, next. It says here, no, you wish you were done. It says the heat of combustion is 44.6 kilojoules per gram. We want to write out a balanced thermochemical equation for this combustion of the fuel. So we do want to do that. Calculate its delta CH in kilojoules per mole. It says that it's got a heat of combustion of 44.6, negative 44.6, of course, exothermic, yes, kilojoules per gram. So negative 44.6 kilojoules for every gram that we burn. How are we going to get that into kilojoules per mole? What? I don't know about divide by. Yep. Well, you're going to have to find the molar mass of C6H12, yes? Okay. So we're going to figure out the molar mass by that. Remember, because molar mass is grams per mole, yes? So if we do this, if we multiply it by the molar mass, we're changing kilojoules per gram into kilojoules per mole, yes? Because the grams are going to cancel here. Kilojoules per gram, we're going to be left with kilojoules per mole. What is the molar mass of C6H12? It is what? 80-something, right? 84.18? Okay. Grams per mole. We're going to multiply those two together. It's going to give us a big number, which, of course, you probably would expect for the most part, being that it is a hydrocarbon. We typically burn those, and we will get 3754, negative 3754.428 kilojoules per mole instead, correct? So you would expect to get 3754 kilojoules per mole of energy released when you burn every mole of this, right? Correct? Yes? That is the delta CH. The question does ask us for delta CH here. What is the molar enthalpy of combustion? We'd have to use probably a little bit of significant digits here, I guess, but what is it? Negative 3754.4 kilojoules per mole, or I would say, what, 3, I guess, significant digits. So I guess we better go with 3 here. 3.75 times 10 to the 3 kilojoules per mole would probably be the answer that they're looking for. That's a 3 there, sorry. Negative 3.75 times 10 to the 3 kilojoules per mole. Good so far, yeah? Okay. If I want to write a balanced thermochemical equation for this, and I want to include enthalpy change here in part of this equation, you either need to include it as a term within the equation, potential energy diagram, or delta H notation, one of those three. I'd probably do delta H notation in this case, so I just put the delta H over here. Remember, this is the enthalpy change associated with this particular equation. We're burning 1 mole, so I should have a negative 3.75 times 10 to the 4, or sorry, 10 to the 3. It is Monday morning, so I have had a few issues already today, like so there. That would be a balanced thermochemical equation for that particular one there, yes? Okay? Once again, it's 3754 kilojoules per mole that we burn, and we're burning 1 mole, so negative, well, 3754, but basically rounded significant digits kind of thing, okay? So this would be a balanced thermochemical equation right there for you, okay? Good? Questions, anyone? Questions? All right. All right, moving on then. Well, let's do this one then. Let's start with the diagram anyway, if nothing else, and we'll go from there. Go ahead. Okay, there's your 2-ethyl-1,3-dimethylbenzene there, yes. We need to get the right correct formula here, hopefully. This is kind of important here, because if you don't get this one right, the rest of this question is going to be wrong, obviously. There's a lot to do with this, and it all depends on this. We got 6 carbons, 7, 8, 9 carbons. We got an H there, H there, right? Because remember, in benzene, it's C6H6, but in this case here, of course, those ones there are going to be H's. So that's 6. Oh, sorry, I missed one there. Yeah, sorry. C10. 3, 6, 9, 12, 13, 14, yes? H14. Okay? So once again, yeah, obviously very important. Make sure you get that formula correct. If you don't, what happens is when you go to balance it, because you will have to, they talk about combustion, so C10, H14, and oxygen. Gives you carbon dioxide here, of course, we know that, and water. And balancing, let's see here. I'm going to tell you right now that, you know, if you want to go ahead and balance it right now, that's fine. But you will have to double this one, and I know that because anytime hydrogen here, this is 14. Well, if I put a 7 there, I'm going to get an odd number of oxygens, but they're only even on this side, so that's going to be a problem. So if you double it, we could put a 20 here. Okay, that's 14 H2s. That gives me 40, and 14 is 54. No, yeah, 54, and 27, half as much. Okay? Good so far? All right. So that's the first part here anyway. It says we have 100 grams of this 2-ethyl-1,3-dimethylbenzene. So 100 grams, I'd put that here probably. Okay. They're probably telling me that for a reason. I probably could find, what else could I find from here? I could probably find the molar mass. Yeah. And I could figure out how many moles I'm burning. So let's do that. Maybe 10 and 12.01 and 14 times 1.01. It's 134.24 grams per mole for molar mass. And I could figure out N from that. 100 divided by that. 0.7449 moles of this C10H14 that I'm burning. Okay? So that's good. All right. That's not really, I mean, that hasn't really answered part of any of my question here, but it might help. What else do I need to know here? Well, it says, calculate how much heat is released by the combustion of 100 grams. And they tell me delta FH here. So, what can I do with this now? What do you think? Yep. Well, I was kind of hoping you'd say that actually, because that tends to be the common response, is that people want to take this here, moles, and multiply it by that. But the problem is, this is delta FH, yes? Not delta CH. There's a difference. The combustion reaction, if it was formation, yes, absolutely, I'd say that's perfect. This is a combustion though. So when I tell you delta FH, what do they want you to do? What's the magical term that we should use now? Yeah. What? Loch-Hess monster. Absolutely. We should use the Loch-Hess monster, right? Products reacted. Let's subtract the 2. Okay. Delta H. See, now the problem is, like I said, that is the heat associated with forming that. We use heats of formation to calculate delta H, right? The enthalpy change associated with this equation, but we don't use delta FH for a combustion reaction as far as, just multiplying the 2. So we need to do, yes, Loch-Hess monster. Delta H is equal to the products minus the reactants. Now, why do they tell you delta? Guys, I'll tell you right now, if you see this kind of thing here, delta FH, there's only two questions you're going to get from that. They're either telling you that because they want to speed up the process and the delta FH isn't in the data booklet. Okay, that's why they gave it to you, because it's not in here. This list of numbers that we got from Unit 1, it's not there. You won't find it. Okay, 2-ethyl 1,3-dimethylbenzene's not in there. It doesn't make any mention of that. It's too complicated. Okay, so they're either trying to help you do a formation reaction, and if it's not formation, if it's combustion, I'm telling you right now, it's Loch-Hess monster. Gotta be. Okay, that's the only reason they're telling you that. So, products minus reactants. What is delta H? If we take, what do we need? 20 carbon dioxides. That's negative 393.5 kilojoules per mole. And 14 waters. That's a negative 241. I always mix these up here. 241.8 kilojoules per mole. That's your products. Okay. Minus your reactants. So minus, well, what's my reactants? 2 of these C10H14s. And I know that from the question, of course. That's where my delta FH is going to go into here. It was negative 80 point something. 0.1. 80.1 kilojoules per mole. And what's 27 oxygens? 0, right? Elements are 0, so we don't need to worry about those. Good enough. So there you go. It was 80.1, is that correct? And the question? Well, negative 80.1, yeah. Okay. So let's add these up. And 14 times negative 241.8 minus 2 times negative 80.1. Oops. What did I screw up here? There we go. Negative 11,095. Yes? Yeah? Yeah. Because I have to multiply by the number of, that's balanced chemical equation, right? 2014. Right? That's how many moles of those products I'm making. So 20 moles of carbon dioxide, 14 moles, and that's why I multiplied by that. I get here delta H is a negative 11,095 kilojoules, correct? Yes? Yeah? Okay. So, good. I'm just going to take 1 second here, guys, and I'm just going to write out the equation again, and I'm going to include this this energy change, or basically this enthalpy here, as part of the, not as part of the equation, but I'm going to include this in my chemical equation here. So it was what, 2 of those, 2 C6H14 and 27 oxygens gives me 20 carbon dioxides and 14 waters, and delta H for this is a negative 11,095 kilojoules. C10, sorry, yeah. Okay, all right. So that's a balanced thermochemical equation for this one. We're not done yet, right? Look, 2 moles,
gives me 11,095 kilojoules of energy released, negative, right? Obviously, so exothermic releasing. I'm not burning 2 moles though, because remember, way back up here, I said we're burning 0.7449. So, a couple ways you can do that. You could do the ratio proportion thing, which we kind of did earlier, this unit. I did a little review on that. So I could say 2 moles gives me 11,095 kilojoules of energy released. How many does 0.7449 give me? Could do that. You could use, if you want to be fancy, you could use the formula, delta H equals N delta CH. So how much energy is released by 0.7449 moles times the molar enthalpy of course, C10H14. Well, the molar enthalpy for 2 moles, I have this many kilojoules, so the molar enthalpy is, of course, that, right? Dividing by 2, right? So, 11,095 divided by 2 is the molar enthalpy of combustion of C10H14. That's how much energy I get released per mole. So I multiply those 2 numbers together, and you should get, now, really, I guess I should probably go back up here. Just give me 1 second here. I better do this properly here. 100 divided by 136, 134. Okay. Now, okay. And I'm going to multiply that by, there we go, negative 4132.216 kilojoules. Yes? Is what I got. Yeah, I know. Yeah. Significant digit-wise, we need to take a look at that. I guess I should probably find this question. Where is it here? Well, looks like 3, 3, and 3, right? Everywhere here in the question. So I probably should go with delta H here. Negative 4.13 times 10 to the 3 kilojoules is how much energy I'd expect to be released from burning 100 grams of 2-ethyl 1,3-dimethylbenzene. That's a lot of work. Fun. That's what I call that. Hey? What do you think? Good? All right, here we go. So, this one, methyl ethanoate, when burned on a bomb calorimeter, blah, blah, blah. Calculate delta FH, of course. Well, once again, first things first, methyl ethanoate, we probably need a formula for that, so let's do that first. Let's see. Ethanoate, of course, is the acid part, which came from the acid, which we'll talk about tomorrow. That's the that's the ethanoate, which comes from ethanoic acid. The methyl part came from methanol, of course. So it looks like that. We need to fill in the rest with H's, of course. So H3. Chemical formula for that is what? C3H. Sorry, I need 3 there, don't I? 6. O2. Combustion. CO2. And water. Liquid. Okay. Because it's a bomb calorimeter. In a bomb calorimeter, of course, water is a liquid. That makes a difference because there's 2 different numbers for heats of formation for gas and liquid, of course. Balancing. I'm going to tell you right now, you're going to have to double this one. Okay, so we might as well. You don't have to technically. If you wanted to keep them all at 1, that's fine. It actually gives you 1 less step at the end. It's not a big deal. It's up to you which way you want to balance it. You can balance it based on just this, and you can use a fraction, or you can double it right now, which I'm going to do because that's what I like to do. 6 there. That's what, 12, so that's 6 there. That's 12, and 6 is 18 octets. I have 4 here, so that's 14. That means I need another 7 there. Well, 7 times 14, or 14 there. 14 and 4 is 18 and 18. Okay. This one says This one says that I need to basically find delta FH, the heat of formation, for this one right here, C3H6O2. So to find delta FH, I'm going to have to use, of course, I'm going to have to know delta H. Well, it tells me in this question here that the delta CH for methyl ethanol when burned is this per mole. Okay? If I wanted to basically, it's negative 1592.2 kilojoules. If I wanted to write out a balanced chemical equation based on this, I would have to say that that is probably, let's see here, negative 1592.2 times 2. So this right here would be a negative 3184.4 kilojoules. Okay, that would be my balanced thermochemical equation for this one. Remember, it's 1592.2 kilojoules of energy released per mole that I burn. It says here that I'm burning 2 moles, so I double it, right? That's why I'm doubling that one there. Now, once again, if you balanced it based on 1, then you wouldn't have to double that. Okay, that'll save you a little bit of time there, but it also gives you fractions in there, and some people don't like that. Okay, so just so you know. Anyway, moving on. If I want to find the heat of formation, I know that heats of formation are used in Loch Ness Monster to find delta H. Well, I know delta H for this particular one. It's a negative 3184.4 kilojoules is how much heat energy is released when I burn this. Okay. What is the heats of formation for the products here? Well, 6 times negative 393.5 kilojoules per mole, heat of formation for carbon dioxide, and 6 times a negative, this one is water liquid, of course, so that is, what is that? Water, right there, 285.8 kilojoules per mole. That's my products, okay, minus my reactants, 2 times C3H6O2, okay, like so. And that's what I'm trying to find, right? So that's my missing part that I don't know, the heat of formation for that, and I'm trying to solve based on this equation here. Now, once again, if you didn't double everything, you'd have half of everything here basically, and you wouldn't have to worry about the 2 there as well. You'd have half as much. However, I chose to double it, so that's what I have. You may not have that exactly, but that's okay. Next, I'm going to keep this here, negative 3184.4 kilojoules, and I'm going to add up this stuff here, and that stuff there is what? Let's see. 6 times a negative 393.5 and 6 times a negative 285.8. So that's a negative 4075.8 kilojoules minus that. Okay, so I just basically got the first part together there. Secondly, I'm going to get the C3H6O2 is, I got to solve for that obviously. So to do that, I'm going to add 4075.8 kilojoules here, and I'm going to add 4075.8 kilojoules here. So basically I'm going to get rid of that from this side here, okay? And let's see, that is what? Let's see, 4075.8 and a negative 3184.4, and I get 891.4. So that's a positive 891.4 kilojoules. Okay, and that is equal to, of course, on this side, what do I have left? A negative 2 C3H6O2, like so. How do I get C3H6O2 by itself? I divide both sides by a negative 2. So divide by negative 2 moles here, basically, right? Divide by negative 2 moles here. And dividing by negative 2, I get a negative 445.7 kilojoules per mole C3H6O2. So that is my heat of formation for C3H6O2. Good? Yes, no? I think in the first class I got a different number for that, but I could have just typed in a wrong number somewhere. That's how you do it. Did someone else get that, or did I type it in wrong maybe again? Okay. Maybe I don't remember. Maybe I did get that I don't remember. It was first period. I don't know. Who knows what goes on in that class? Okay. All right. So that's the heat of formation. So delta FH here for C3H6O2 is a negative 445.7 kilojoules per mole. Okay? Good? Good. Next. This will be new for you. Okay? Addition reactions. Next. So here we go. That's all review stuff. That's the easy stuff, right? Here's the new stuff. This is the addition. Unsaturated hydrocarbons can become saturated. What do they mean, unsaturated? What is unsaturated? Somebody. Huh? Sure. Double or triple. Yeah, double or triple bond can become saturated. What does that mean? Single bonds. So double or triple can become saturated, single bonds, through addition reactions. Okay, you need to quit talking. These reactions involve the atoms of the small molecule being added to the carbons of the double or triple bond. So in these organic compounds, we have double or triple bonds, and that small molecule there, that add-on addition part, is going to get added on. Okay. Now, I need to get rid of that. Okay. So adding hydrogen turns alkenes into alkanes, for example. Alkenes is double bonds. So here's your double bond here. This double bond will break. One of those two bonds will break, of course. We can't break both of them, otherwise we're not going to have our carbon chain anymore. But this bond will break here and form an electron here and an electron here. Because remember, those bonds are really just two shared electrons, yes? So those that bond is going to break. You're going to get two free electrons there. And guess what? There's also hydrogen here with two electrons there. And what happens is basically those, once again, that bond is represented by two electrons. This will share with that one there, and this one here will share with that one, for example, and they will get added into the chain, hence the term addition, believe it or not, addition reactions. The thing with addition reactions is these reactions sound exactly like they are. We're doing addition today. Tomorrow, we're going to look at elimination, so we're going to take stuff off. We're going to eliminate stuff. And substitution, we're going to switch them around. And then, of course, esterification, which is acids and alcohols. Okay? So, next here. Ethene and hydrogen is an example of addition reaction. Let's take a look. What does ethene look like here? Well, ethene is what? CH2, I guess. Double bond CH2, yes. And hydrogen. So you're going to draw this out, guys. This is what you guys are going to do today. And this is what we want to see. You're going to draw these out like so. CH2, CH2, and hydrogen. And what do you get as a product? Well, this double bond, like I said, is going to break here. So you're going to add another hydrogen onto this one. And you're going to have a single bond now. And you're going to add the other hydrogen onto this one. So hydrogen goes there. Hydrogen goes there. On either side of the double bond. It always goes on either side of the double bond like that. And you get CH3 and CH3. And you're going to name your products as well. So we're going to call this, of course, ethane. Okay? You have to name your products as well. So you're going to draw them out. Then when you're all done, you're going to name them. Okay? Ethane. Good? Questions? That's not...
There's two electrons in the hydrogen, right?
Yeah, well, those two electrons are attached here now, right? These two electrons here, there's one here, there's one with this hydrogen, they share now. Yeah. Okay? The addition of a halogen produces an alkyl halide, so we can add in some halogens. Halogens, of course, group 17 stuff, like, for example, chlorine, chlorine is an example of a halogen. Fluorine, fluorine, bromine, bromine, iodine, iodine. Okay? And you get alkyl halides, right? Those are the ones with bromo, fluoro, chloro, frodo, Guillermo, no, All right, so for example, like cyclopentene. Cyclopentene would look something like this here. I'm just going to put the double bond there because I want to. Cyclopentene and chlorine. What do you get as products here? Well, once again, double bond breaks. Chlorine has 2 free electrons. That's what's holding them together, of course. So when that breaks, they're going to get added on here and here, right? On either end of the double bond. Because remember, 1 electron goes to that carbon, 1 electron goes to that carbon. Chlorines add themselves on. We need to name this still. So the name of this one would be 1,2-dichloro cyclopentane. 1,2-dichlorocyclopentane. Good? That's not bad. Good? Yes? Okay, moving on. Now, this is often a diploma type question here that for sure they'll talk about. Usually they have something about this bromine thing here. So a simple addition reaction using bromine can be determined whether it's a saturated hydrocarbon or an unsaturated hydrocarbon. Because Br2 linked together, when you have Br2, Br, when they are linked together like this, in an aqueous solution, in a water, this is an orange color. Okay? So this Br is an orange color when it's placed into water. When you add that on to a unsaturated hydrocarbon, such as a double bond or a triple bond, of course, that Br gets added in, right? But it doesn't stay together as Br anymore. 1 Br gets added on here, 1 Br gets added on here. It's not Br2, they're not linked together anymore. When they're linked together, it's orange. When they're broken apart, it's clear, okay? So if you actually add this into a long chain, the Br2 that was linked together that's orange is now Br here, added onto that chain, and that doesn't have a color associated with it. So if it's got a double or a triple bond, addition reaction will happen quite quickly with bromine, and that color will disappear, okay? So that color will quickly disappear and become basically clearish color or whatever happens. So when it reacts in an addition reaction, the orange color disappears quickly at room temperature as the bond between the bromine atoms breaks. So when this breaks and you get Br like that, and it's added on somewhere over there to a chain, that orange color disappears. So we can use this quite often to determine whether the hydrocarbon we are dealing with is saturated or unsaturated. Okay? If it's saturated, that's not going to take place. If it's unsaturated, it will take place. Okay? So look, here's an example. The reaction between pent-2-ene and bromine. Here's a double bond right here, right? So this double bond is going to break. You're going to get 1 here and 1 here, and the bromine will add on here, and the Br will add on here, and you will get that looking diagram over there. In this case here, of course, the orange color is going to quickly disappear because you're breaking the Br to Br bond. You're breaking this, okay? So orange color, you guys I think have this on your page there. Orange color disappears quickly. I think that's on your sheet. If it's not, write it down. Okay? So in that case, the orange color would disappear. But, once again, that's an addition reaction where you're adding bromine and bromine in. Here's an example of pentane and bromine. Well, pentane and bromine, there's no double bond here for this to add into, right? So there's no double bond, so therefore there's no addition in this case. Okay? And in fact, we're going to talk about this another day here, probably, well, actually, not when I say another day, I mean tomorrow, because that's the only other day we have of reactions. So we're going to talk about this one tomorrow, what would happen here. But there's no place for the Br to quickly add into this. this bond is going to stay together, so it's going to stay as an orange color. Okay, the orange color is going to persist or stick around, basically. All right, that's how you can tell hydrocarbons are saturated or unsaturated. Okay, add bromine and see what happens. All right. So next, addition of a hydrogen halide. So for example, hydrogen halide like HCl or HBr or HF or HI, when you do this though, what happens is you may get more than one product being formed. Okay, so we're gonna kind of introduce you to the first of many where you may get isomers. Because before, you know, we basically were adding the same thing in. But now we're adding two different things in. We're adding an H, and for example, in this case, a chloride. So let's do this one. But 1-ene, okay? This would be what? H2, H, H2, H3. And hydrogen chloride. So, what's going to happen here? Well, we need to add in probably addition, obviously. Double bond, we're adding stuff on. So that double bond's going to break. We're going to add an H, and I'm going to add a Cl on. So the question becomes, now, you don't have to write this quite yet here, guys. Just give me a second here. Okay? So let's say that double bond right there, that bond right there breaks. So I can add an H onto this one and a Cl onto this one, right? Because that bond breaks, there's two electrons there. One electron here, one electron here. H gets added on here, Cl gets added on here, yes? Good? Yeah.
What we do with anything that's like need 2 inches and H2O?
Well, just wait. H here, yes? Or H here, Cl here, yes? Good? Okay. So that's what it would look like. Of course, you wouldn't write it like that. That looks goofy, right? We've never done that before. Don't do that. Okay. You need to include all the H's together. So I would say that's probably not a good thing to do. But this is CH3. That's fine. Cl, CHCl, CH2, CH3. So there you go, right? But my question is, I guess, or one of the things that comes up here is, well, right? Who's to say that the H went here and the Cl goes here? What if the Cl goes here and the H goes here? Is that different? Can that happen? Yeah, the answer is it can happen. Who's to determine that, right? So maybe the Cl goes on this one and the H went on this one here instead. Okay? So we get what we call isomers, of course. So writing that one out, of course, we're going to get slightly different here. So this would be what? CH2. This is going to be CH2, CH2, CH3. Okay? So that's an option as well. And these, of course, once again, same structural formula, same chemical formula, right? C4H, whatever it is there, 6, 7, 8, 9, Cl. So same formula, but different structures. So we call these isomers, of course. This would be, of course, you're going to write these out here, by the way. 2-chlorobutane. You need to name these as well when you're done. And 1-chlorobutane. And you know what? When you're done naming them, I guess the answer is, how do I know if I get isomers? Well, if you're done naming them and drawing them, and if you have different names for them, I guess they're different, right? Otherwise, they'd be the same if they had the same name. So, can you flip it around? Can you turn it over? Can you flip it over? Do you get the same thing? No, not in this case. So you got more than one possible structure here. Okay? 2-chloro, 1-chlorobutane. All right? So that's what happens when you take, for example, but-1-ene and hydrogen chloride. All right? Good? Next. What about but-2-ene? You know what? This is kind of... Let's do it down here. Get rid of that there. And hydrogen chloride. Let's see, that's 3. That's 1, 1, 3. Okay? So but-2-ene and hydrogen chloride. What happens here? Well, we get CH3. I'm going to put my H here. I'm going to put my Cl here. Okay, so H there, Cl there, and CH3. Is it any different if I switch those around? So do I get a different name? So I'll do it real quick here just to show you. CH3, I'm going to put my CHCl here, my CH2 here, and my CH3 there. Are those two different from one another? Or are they the same? They're the same, right? They're just flipped around. Do you agree that both of those are still 2-chlorobutane? Right? So in this case, whichever one you decide is going to be your only option here. So 2-chlorobutane, we don't need that one because it's the same, right? They're both 2-chlorobutanes, so there is only, in fact, one possible structure for this one. Okay? Yes? Because remember, you gotta name them, and you gotta name the chloros as quickly as possible, right? Because that's the add-on here, so it's got to be 2-chloro this way or 2-chloro that way. They're mirror images of one another. So 2-chlorobutane, that's all you need to have. Do not write the other one if that in fact happens. Okay? So that's all you need to have for this answer. 2-chlorobutane. The addition of water produces an alcohol. So we can add in water to a double bond, and we can get an alcohol. So let's take a look at that one. Pentuene. Let's see here. Let's let you guys do this one. Okay. So pentuene looks like that. We're going to add in some water, HOH, H2O. Well, let's see. Addition. So let's put on the H. Let's put the extra H here, and let's put the OH here. Okay. And then these will be the same. Is there another option? What happens if I flip those ones around? Do I get the same thing or is something a little bit different? So let's see. What if I put CH3 here, of course? Now this is a CH here already. What if I put the OH here and the H over on this one? And CH2, CH3. Okay? So those two are of course different. They have different names. You can't flip this one around and get the same name. This is called pentan 3-ol, and this of course is called pentan 2-ol. Okay? So you need to obviously make sure you guys, when you're done drawing them, that you make sure you guys include the name that goes with them as well. Okay? So pentan 2-ol, pentan 3-ol. You have to draw all of them, yeah. These are going to be questions on your test and on your diploma, and they'll give you, basically what they'll say is maybe something like this, similar. They'll have about 4, maybe 8 different structures to pick from, or 8 different names, and you'll have to tell me all the products that are associated with this. So, you know, eventually we're going to get to, when we start doing this stuff here, we're going to get to ones that have 4, 5, 6 different isomers as answers. So you're going to have to draw 6 products, and then, or maybe what this one particular one that I'm thinking of has 4, and you'll have to, in the numerical response, pick out the structures that match those ones up. So maybe they're just the names, or maybe they're the structures, or whatever the case might be. But, you know, for example, for this one here, we could assume maybe there's another 2 structures, pretend that there is. You could say, well, this is the second one, this is the 4th one, this is number 7, this is number 8. Write those down in numerical response, the ones that match up with these structures. Something like that. Or names, pentan 3-ol, pentan 2-ol, you know, pentan 1-ol, or something like that, and then give you some other options. And once again, write out, you know, what you think the answers are. So it could be numerical response, could be multiple choice, pick the right answers, whatever. Those are all possibilities. Those are all good diploma-like questions, kind of thing. And you'll get some practice like that if you do Quest A Plus and Key Booklet and stuff like that.